Hello everyone, and welcome to the Neotech Electronics Series. This episode is going to concentrate on the common emitter amplifier. So let's get started. Alright, so let's start this. Let's start the discussion of the common emitter amplifier by first going over the linear amplifier. So basically, a linear amplifier provides amplification of a signal without any distortion. So the output signal is an exact amplified replica of the input signal. All right. So let's just talk about how we write an amplifier or draw an amplifier to do that. So we come in here. Right? Come down. There's your first resistor, right? Here's your transistor. We use a bipolar junction transistor in this case, right? I'm going to draw another resistor right here. Ground, right? And remember, here's your base that comes right off here. So remember, this is your base, this is your collector, and this is your emitter. Alright? Hence, since this is your collector, we're going to call this resistor up here R sub C for your collector resistor. This resistor here is going to be called or labeled R sub E. Now your base is biased via a voltage divider, alright? So what we'll do is we'll bring something out here, bring it down. This is another resistor here. Comes straight down. You got it connected here. Then we're going to continue this, come right down. We're going to do another resistor, down, and then over. Alright, these are connected. These points are connected. Now, these two resistors, which we're going to label R1 and R2, are simply used to provide a bias voltage on the base. Alright? By the way, up here is VCC. So you have a voltage here, it goes through this resistor, and then it's at ground, right? So hence you have a voltage divider. Generally, the value of these resistors are approximately 10 times or more the values of the resistors used here. So very little current goes through this side of the amplifier. Now let's continue taking the base out here. By the way, it's all connected right here. Your input signal is going to come in through this coupling capacitor. I'm going to call this C sub 1, right? And it comes out, and then it comes into your AC source. That's your AC source, and then that's going to be connected to ground. Alright, so this side over here is your input. Let's look at your output, shall we? We're going to, in this case, we're going to tap off the collector. Here's the capacitor. This is a coupling capacitor on your output. We're going to call this C2. C2 then is going to be connected to your load resistor, R sub L, and then this is going to come down and be connected to ground. Alright, so there is your linear amplifier. linear amplifier. Okay, there you go. Now, as we said, a voltage divider bias transistor, right? That's what we have here. It's biased by this voltage resistor. That's your base voltage, which is capacitively coupled to the base through C1. Here's your input, which is capacitively coupled to your base, right? And the load resistor is capacitively coupled through C2, right here, right? We said that when we were drawing it. I just want to emphasize that, right? The coupling capacitors block DC, right? We know that DC voltage will not go through a capacitor and is seen as an open, all right? So this prevents the internal source resistance, which you're always going to have on a source. You're going to have RS here and the load resistance RL from changing the DC bias voltages at the base and collector, all right? That's what those capacitors are there for. All right, the capacitors ideally are seen as shorts to a signal voltage. So here's the other thing about a capacitor, right? Let's just write down what we just said, right? So DC, a capacitor is seen as an open. AC, it's seen as a short. So what this means is this AC signal can pass through this capacitor, and then basically it's going to ride on top of this DC voltage, right? And that's going to allow the AC signal to be amplified, and then when it goes through this capacitor here, that DC voltage is going to be stripped off, and you're just going to be left with the amplified AC signal, right? The sinusoidal voltage causes the base voltage to vary sinusoidally above and below its DC bias level. The resulting variation in base current produces a larger variation in the collector current because of the current gain of the transistor, right? So that pretty much is your linear amplifier. One thing I want to be sure to say regarding the AC signal and the capacitor acting as a short. We talked about the critical frequency. So there is a frequency range where the capacitor is seen as a short. I just want to make sure that that's understood. That we're going to talk about in future videos. But in this analysis, we're assuming that the AC signal is at a frequency where the capacitor is viewed as a short. All right, everybody. Now that is the linear amplifier. And the next part of this episode, we're going to discuss the common emitter amplifier. And it's very similar to the linear amplifier. Thank you. Alright everybody, welcome back. So, I modified our drawing just a little bit because this currently is the linear amplifier. Now what I did is I changed this capacitor number from C2 to C3. No big deal. But I did that because a lot of times it's listed like this in the literature. But think about it. If this is capacitor 1 over here, that's your input coupling capacitor. Capacitor 3 is your output coupling capacitor. Where do you think capacitor 2 is going to go? Well, that's the $64,000 question, right? And let me just draw it for you. It's right there. Just just going to bring it on in here to ground. This right here is C2. And this is known as your bypass capacitor. Bypass capacitor. Now, listen very carefully. This is the common emitter amplifier. Now, what that means is the emitter, right? So when we talk about the emitter, we're talking right here, right? The emitter. The emitter is common to both the input and the output, okay? That's very important to remember, or to know, because they have a common collector amplifier as well, right? So I believe they even have a common base amplifier. They have other things that are common, right? So there are three configurations: a common emitter, common base, and common collector. Okay, yes, I just read that while I'm talking. So they have all three types. So the common emitter means the emitter is common to the input signal and the output signal. Now, in the last section, we just finished stating that for an AC signal, as long as you have the right frequency range, it's seen as a short. So if you have a signal coming through here, let me just draw that in red, okay? So if we have a voltage signal coming through here like this, right? This is your voltage in, V in, okay? Now it's a great, the frequency is in the right range for the capacitance to be seen as a short. That means then this capacitor down here, I have to find where my pen is. There we go. This capacitor right here, C2, right, is going to be seen as a short. That short is going to bypass this resistor RE. Got it? So if this shorts this, it's like this resistor isn't even there for the AC signal. Hence, you can see now that the emitter basically is tied directly to ground for that signal. Got it? So there is no signal at the emitter because the bypass capacitor effectively shorts the emitter to ground at the signal frequency. There you go, right? All amplifiers have a combination of both AC and DC operation, which must be considered. But keep in mind that the common emitter design refers to the AC operation, okay? So that's the first thing. That's why they call it the common emitter. Next thing, let's talk about phase inversion real quick. So if your signal comes in as I've drawn it here, right? Where am I here? If it's drawn just like it is right here, right? That's your input. Now, if we want to draw the output, if we want to look at your current, I'm going to make that in blue. Your current over here is going to be about the same. It's going to look the same, isn't it? And I'm going to call that I. C for your collector. So you can see that when your voltage goes up, and this makes sense, doesn't it? If you have a voltage coming in here, and your voltage is coming in here, it's just like this, passes right through that capacitor. You see your base is going to have this same type of curve. It's going to go through your emitter. This is like a diode, so it's going to give it a 0.7 volt drop, right? A reduction in voltage, assuming it's a silicon transistor, which it is. So then your voltage here at your emitter is going to look the same, right? Now, here's the thing. Your current going through here, if your voltage goes up, right? Since your resistance here is constant. If it goes up, that means your current is going to increase. If your voltage goes down a little bit, that means your current is going to decrease. Get it? So your current is going to do the same thing as your voltage, right? But look at it in this way. So here's your current. We just drew the current. If your current is going to, this is your current right here. If your current is increasing, this voltage here at your right here, no, I drew current, but if your current is increasing, we're going to say that this voltage here, let me change that so it's the right color, that voltage is going to decrease. Well, let's look at it. Remember, you're starting with VCC, aren't you? So VC, your voltage at your collector, is going to equal VCC, obviously that's what you're starting off with, minus the drop across RC. And that's going to equal IC RC, right? And I should have made that a minus sign there. Sorry about that. That's a minus sign there, right? This is what the interesting factor here. Because notice, when your current increases, this is a larger value. If you subtract a larger value from VCC, that means your voltage gets smaller. This means now that your voltage is going to look something like instead of this, that's your current, and instead of this one, which is your input voltage. So you notice this is 180 degrees, right, out of phase. With the input. All right? So those are two takeaways I wanted to make sure that you have when looking at the common emitter amplifier. One is this phase inversion we just talked about here, that right there. And the other one is that the emitter is common to both the input and the output. And I don't know if I said this to you earlier. This load, this is your output over here, obviously. This amplifier is to power this load, is to supply voltage to this load. So that's what it means. And to mean that it's common to it, that means that ground, obviously both of these are oscillating around ground, which that's your common point, because your emitter is for that signal passes right through it and is connected to AC ground. All right, I hope this helps you. And next we're going to talk about further analysis of the common emitter amplifier. Thank you.